Hello and welcome to Morehouse's Math Menagerie, where outliers are always welcome. Today, we're going to be talking about how to organize and display data. But before we start, I just wanted to ask you, do you know which side of a chicken has the most feathers? The outside. All right, jumping into data here, we have some characteristics of numerical data. Numerical data has a center or a typical or expected value that kind of represents the middle of the data set. It also has variability, the spread of the data. We'll get more into these two terms later, but for now, there's general ideas of how data behaves. The distribution is the shape of the data set, and outliers are pieces of data that are far away from the majority of the rest of the data. Again, a little bit vague for now. We'll come back to these in a little bit. A frequency table is a way that we can organize data. It's a table that shows you how frequently something occurs. Hence the name frequency table. You can see over here, we have a variable I color and then 4 values of that variable. On the right-hand side here, we have the frequency that each of those values has. So 166 students had blue eyes, 177 brown, and so forth. Now, if you think a frequency table is crazy, wait till you see a relative frequency table. The term relative in statistics often refers to the fact that we're going to put things in percentages or proportions. So here we have the same variable I color with its 4 values. But now the frequency is put into percentages of the total instead of counts out of the total. Let's talk about how to make a frequency table. So we have a bunch of data here for drive-through service times in seconds for a local fast food restaurant. The first thing we're going to want to do is identify the smallest and largest values, which I believe are 83 seconds and 308 seconds. So that's about 200 apart, 250 apart. We want to create bins to put these values in. So I think we're going to start at like 75 and go every 50 seconds to make bins. And so if we did that in a frequency table, we would get something that looks like this. To make life easy, we started at 75, and then we went about 50 values, 50 seconds up, and then started another bin, and so forth until we reached 325. And this covers all of the data values. You can see there were 11 times that were between 75 and 124 seconds, and 24 that were between 125 and 174, and so forth. Now, this is pretty intuitive, but of course we can't keep it simple. We have to give it a bunch of vocabulary. So the 75 is termed the lower class limit for that bin, and the 124 is the upper class limit for that bin. The class boundary is the number in between 124 and 125, so 124.5, just for fun. And then we have a midpoint of a class, which would be the average of the upper and lower class limits. And so, for instance, this second bin, the class midpoint is 149.5. Now, in practical sense, none of these terms matter, but you might have to know them on a homework or something, so pay attention to that. Oh, we also have a class width, I almost forgot, of 50. How exciting. All right, now we have a frequency table, and then we also have something called a cumulative frequency table. The cumulative frequency table does just that. It accumulates the values. So we would start with 125 and say, okay, there's 11 values less than 125. When we jump up to the next upper class limit of 175, we would add the 11 to the 24 that are between 125 and 74. So there are 35 fast food times that are 35 values or less. And then the same with 225 and 275 and 325. By the end, we should have all of the values. So all 50 restaurant times are less than 325. Now, a table's nice, but what's better than a table is a graph. So here we have a histogram. A histogram is a visual representation of a frequency table. So here you can see that between 75 and 125 on this histogram, we have 11 fast food times. So this bar here is 11 high. Between 125 and 175, we had 24, so the bar goes up here to 24, and so forth. The important thing to remember about a histogram, it is not a bar graph. Bar graphs are for categorical variables like eye color, where histograms are for numerical variables, kind of like fast food times. These bars represent an interval of time, 75 to 124, and so forth. Now, if a value landed right on 125 seconds, we would put it in the upper bin and not the lower bin. So each bin goes right up to 125, and then once we reach 125, it would jump into the higher bin for each of these. Now, the width of the bin is negotiable. The last one, we had the bin width of 50. Here's a histogram of the same data with a bin width of 25. It still looks pretty reasonable. We get more bins, of course, more bars, but it still is a pretty good looking graph. Well, we could go down to bin widths of 15. Getting a little bit messy here, but not bad. We can still see a general shape to the data. It's not too bad. Now, if we went down to bin widths of 10, you can see there's just way too many bars here. There's a bunch of gaps in between. We're getting too into the details here. Histograms are intended to give a general shape and look at the distribution. It doesn't need to be this detailed. So something like the 25 is probably the best. 50 was okay, but 25 gives a little more detail without getting too detailed like the 15 and the 10. So when you're making a histogram, you just kind of want to use your best judgment on how wide you make those bins. Back to the shapes of distributions as we discussed at the beginning. There's 4 main shapes that we discuss in this stats class. The first one is being symmetric or normal distribution. Now, a normal distribution is a very specific type of distribution that is symmetric, but not all symmetric graphs are normal. So you have to be a little bit careful there. You might have heard the normal distribution referred to as a bell-shaped. So we get a nice symmetric look, and there's some other qualities that have to be true about it as well, which we'll talk about in a later lesson. The second type of shape is uniform, where we have basically just a flat line like a plateau across the graph. Everything is uniformly distributed or about the same across the distribution. Thirdly, we have what's called skewed to the right. You can see it's a little bit like the symmetric graph, but this tail to the right has kind of been pulled out. There's like a bit of a slope here that's not as steep as the left side. So this would be skewed to the right. Let me move that out of the way. And then the last one, if we have skewed right, you betcha we got skewed left. So here, same thing, kind of symmetric, but you see this left side, this tail's kind of been pulled out. There's a bit of a slope there. It's not quite as steep as the right side. So this would be skewed to the left, is how we would describe that shape. Now, there are lots of distributions that are just messy. They don't have a specific shape name to them, and that's okay because data is what data is. So if you see something and it looks like one of these, that's great. If it doesn't, it's okay to say, hey, it's just kind of messy. Now, one way we can test data to see if it's normal is we can make a normal QQ plot or a normal quartile plot. When you graph a distribution and you want it to be normal, what we're hoping is that it forms an approximately straight line. You can see this has a little bit of a curve to it. These dots have a curve that don't quite meet that red line. So it'd be a little bit questionable whether or not we'd want to call that normal or not. We'll talk more about this later as well. All right, types of graphs. But before we begin on graphs, do you know where fish get their money from? The riverbank. All right, this graph is a dot plot. We talked about it in class. It's a dot plot because it has dots on it, and it is a good descriptor of a numerical variable. We have a nice horizontal axis here, and we have dots representing the values of the distribution. This particular dot plot is of the heights of high school students. You can see it's fairly symmetric, but we have a little bit of tail to the left. So you could argue a little bit skewed left, but mostly I would call this fairly symmetric. All right, this graph is of the same data, and it is called a stem plot. Now here, what's happening is the stems are these numbers on the left-hand side, 5, 5, 6, 6, 7, 7, and so forth. And the numbers on the right side of this colons here are called the leaves. So let me get a little pen here to draw. So this 4 right here gets attached to the stem and represents the value 54. My apologies for the bad writing. I'm writing with a mouse, so it's going to look kind of messy. And then each of these leaves, like this 0 right here, would be attached to the stem 6 to give us the value 60. Same with this 0. We would have a 60 in here as well, and then a 61, a 61, a 61, a 61, a 61, and then a 62, and so forth. So each of these single-digit values on the right gets attached to the stems on the left to create a number. As one last example here, this 5 would be attached to the 7 to form a 75 in our data set. Now, you're not going to see a whole lot of stem plots out in the wild. These are pretty antiquated. When these were first invented is when we used typewriters. And so you could type these out on a typewriter because we didn't have computers yet. After we invented computers, we got histograms and dot plots and all kinds of awesome stuff. And so stem plots really aren't something that's used anymore. If you ever think to yourself, man, I should really use a stem plot to graph this data, just don't. Use something else. There's so many other quality graphing tools besides stem plots. All right, bar chart. I mentioned these before. They're 4 categorical variables like eye color. And you can see that the heights of each bar represents the number of individuals that have each value of the variable brown, blue, hazel, green, gray. You will see these sometimes where instead of the number of individuals for each category, you'll have a percentage of the individuals who have each color of eyes. That would be a relative frequency bar chart. Oh, I do want to say that sometimes these are called Paretos. I don't know whoever calls them that. It's just something that's in the book. Pie charts. Who doesn't love a good pie chart? Now, I will say we have to hold strong with this one because there's been a movement currently that in textbooks, they are starting to call these circle graphs. Dumbest thing I've ever heard in my whole life. This is a pie chart. Again, these are just for categorical variables, and the slices of each piece here of the pie represent the proportion of the distribution that has each value of the variable. So we can see here this red area is 34.3% of the total pie because that's how many people have blue eyes. This blue area represents the brown eyes, and that's 36.6%. This is just a good way to glance at something and get kind of a proportional understanding of who has what eye color or what value of the variable. Now, you thought pie charts were cool. Here's the same thing, but a donut chart. Again, the same idea. We just have like a hole in the middle. It's not like an apple fritter kind of donut, more of like an old-fashioned kind of donut. But, you know, a donut's a donut, and no one's going to complain because they're tasty. Right, a time series graph is also sometimes referred to as a line graph. And time series basically just indicates that one of the axes, usually the horizontal axis, it refers to time. And so here, this is actually a line graph of the Iditarod race that's up in Alaska and the winning time in days for the race. You can see that early in the 70s and 80s, a lot of variability in times, and we've kind of smoothed out and become more consistent over time. All right. Now, graphs are great. They're intended to give people an intuitive understanding of data. You're supposed to glance at them and just kind of understand some things. Because of that, they can be used to trick you. For instance, this is the bar chart we made a minute ago that we talked about with eye color. Now, if we messed with the vertical axis here and started it somewhere else, we could make it look like brown-eyed and blue-eyed students have a huge discrepancy, when in reality, in the original, you can see they're fairly close. So be careful of graphs that have axes that don't start at 0, especially vertical axes. Sometimes they're trying to trick you if they're doing something like this. Another thing we have to be careful of is using pictures to represent proportions. Now, they took this 1970 data and decided to represent it as a giant cigarette for some reason, and then the 2013 data as a smaller cigarette. Now, 37% compared to 18%, you would think, oh, that's half the size. So what they did is they made it half the height and then scaled the width by half as well. But when you're using area, the area here looks like 1/4 of the size instead of 1/2 of the size. So using three-dimensional pictures can communicate something that is not true. It should be half, not 1/4. Oh, we have our lovely pie chart here. Remember, this is a pie chart. And oh, look, we made it fancy by making it three-dimensional. This is not good. Remember that we're supposed to intuitively look at this graph and look at proportions of red and yellow and green and blue areas and a little sliver of orange. When we made it three-dimensional, we added this red crust here along the front. What that does is it makes it look like the red is even larger than it should be, even larger than this blue almost. And so it throws off the proportionality. Yeah, it might seem fancy. Don't do it. Oh, here's some bad graphs. Here's a bad bar chart that someone put out during COVID. I don't really understand what's going on with this. Just soak in all the badness here for a second. Here's an awesome bar chart where they decided to use human-sized figures for these. It makes it look like people in the Netherlands are like the Jolly Green Giant, and people from Indonesia are like hobbits or something. I'm not really sure what's going on here. But again, using bars and having an appropriate scale over here, not starting at 5 foot, would be much more appropriate than whatever they did here. Again, a bad pie chart. It's not three-dimensional, but not quite adding up to 100% here, so something funny is going on. Make sure your pie charts add up to 100%. Oh man, 2 problems with this one. Number 1, they're lying to you and they made the no slice smaller than the yes slice when they really should be reversed, and it's three-dimensional. Just don't do it. Now, this is a funny cartoon. Dilbert's hilarious, but there's a sliver of truth here with this, because if you're in a meeting and you make a really nice graph trying to convince people what you want to do, if they don't understand the graph, then they could just go along with what your interpretation of the graph is. So use this for good, not for evil, but graphs are a great way to convince people of things. Here's an example of how someone tried to use a graph to convince me to buy their product. At my high school, we had a meeting where this company wanted us to have our students use their program to increase student scores on the SAT. And they said, okay, well, if a student takes the PSAT and they do nothing, and they take the SAT, they get a 60-point increase. If they took the PSAT and then they do our official SAT practice program for just 6 to 8 hours, look, they get a 90-point increase. If they do our program for 20 to 22 hours, they get a 115-point increase. You should buy our program so that your kids can get a 90-point increase. Now, while listening to this salesman pitch this to our school, I raised my hand and said, you're lying to us, because students get a 60-point increase for free for doing nothing. So their program does not give us a 90-point increase. It really only represents the 30 points that go above this 60. The salesman didn't like me pointing this out because it kind of ruined his pitch. But the truth is, he was using this graph to be deceptive towards us and try to sell his product, which is his job, so I'm not mad at him about it. But we have to be able to recognize what's going on in graphs so we can be critical thinkers and not get sold a product that doesn't work. All right, that was me throwing a lot of stuff at you all at once. I'm sorry if I moved quick, but I didn't want you sitting here watching a super long video. I hope you found this useful. Thank you for watching it. Have a great day. Don't forget to jump into the homework and practice this stuff and ask me questions at the next class. Thank you. Goodbye.